Welcome to Tungal Online Classes. Today we are going to discuss the topic of force between two straight current carrying conductors. Two straight parallel current carrying conductors. So already we discussed if any one of the current carrying conductor is placed in the uniform magnetic field over that current carrying conductor some magnetic force will be acting. That concept already we know, but here we are going to discuss that whenever two current carrying conductors are considered, in between those two current carrying conductors they are saying that some force will be existing. Now we are going to derive what is the expression that force existing between the two straight parallel current carrying conductors. So instead of two straight current carrying conductors, first I was considered only one of the conductor. Instead of two conductors, first I will consider what? Only one of the conductor. So let us consider the first current carrying conductor. Which is saying as conductor AB. So out of the two straight current carrying conductors, first how many conductors I considered? Only one of the conductor will be considered. It was named as what? AB. So in that first current carrying conductor, I am assuming that I1 amount of current will be flowing. So instead of two current carrying conductors, we consider only one of the conductor, that is the first conductor. That is what? First conductor, which is named as what? AB. In that first current carrying conductor, what I assumed that I1 amount of current will be flowing through it. In the previous classes, we discussed the application of the Ampere's law. What is the application of the Ampere's law? Whenever you consider a straight current carrying conductor, through this current carrying conductor, whenever I amount of current will be flowing, so around the current carrying conductor, magnetic field will be developed, and the intensity of the magnetic field at a given distance of small r is given by, we derived that B is equal to mu naught I by 2 pi r. B is equal to what? Mu naught I by 2 pi r. This is the application what we discussed in the case of the Ampere circuital law. So the application of the Ampere circuital law states that whenever I amount of current is flowing through the straight current carrying conductor, around the current carrying conductor, magnetic field will be developed, and at a distance of small r from the straight current carrying conductor, the magnetic field intensity expression is given by B is equal to mu naught I by 2 pi r. Similarly, here also, I consider one of the straight current carrying conductor, through that conductor how much current will be flowing? I1 amount of the current will be flowing. So from the first current carrying conductor, at a perpendicular distance of small r, so I want to calculate the magnetic field intensity, which is developed by the first current carrying conductor. So what I consider here? I consider a particular point which is at a perpendicular distance of small r, from the first straight current carrying conductor. At that point I want to know the magnetic field intensity value. So similarly, already we wrote the formula for the magnetic field intensity. So if you apply the right hand thumb rule, the magnetic field will be acting into the plane of the paper. That direction will be, I represented here, vertically downward direction. So the magnetic field intensity at that respective point will be given by, I am indicating that B1. Why I put B1 here? Because we considering two straight current carrying conductors. So B1 is indicating that the magnetic field intensity which is produced by the first conductor, So therefore B1 is equal to mu naught into I1 by 2 pi r. B1 is equal to what I write? B1 is equal to what? Magnetic field intensity which is produced by the first current carrying conductor at a distance of small r from the first conductor. So around the first current carrying conductor, magnetic field will be developed. Magnetic field will be developed. Now I consider the second conductor. I consider the second conductor which is parallel to the first current carrying conductor. So initially I didn't consider both the conductors to understand more easily. First I consider the first conductor. By that first conductor, magnetic field will be developed. Magnetic field will be developed in the magnetic field which is produced by the first conductor. In the magnetic field which is produced by the first conductor. Now I am placing the second conductor. In this second conductor, we are assuming that I2 amount of current will be flowing. In the second conductor, how much current we assume to flow? I2 current will be flowing. Now this second conductor is placed in the region of the magnetic field which was formed by the first conductor. So already we know the basic principle. Whenever any one of the current carrying conductor is placed in the external magnetic field, by the field it is exerting some external force. So that formula also we derive the force experienced by any one of the current carrying conductor which is placed in the external magnetic field is given by F is equal to BIL. Maximum force I consider. So here B denotes what? The field in which the second conductor will be placed. So here in the place of B I will put B1. Why? The second conductor was placed in the magnetic field which is produced by the first conductor. That's why I put B1 and. So I refers to what? The current which is flowing through the conductor, which was placed in the magnetic field of B1. So which conductor we placed in the magnetic field? Second conductor was placed. So that in the place of I, we have to write I2. Don't confuse. B1 is refers to what? Magnetic field which is produced by the first conductor, and I2 refers to what? The amount of the current which is flowing through the respective conductor that was placed in the external magnetic field. So I will write force experienced by the second conductor whenever it is placed in the external magnetic field which is produced by the first conductor is given by B1 into I2 into L. What L denotes? L denotes that the length of the given current carrying conductor. Here we are assuming that both the conductors are identical. Identical in the sense means that both the conductors are having the same length. Now, so this is a force experienced by the second conductor due to the first conductor. So that notation I was represented with F21. F21 is denotes what? Already in the relative motion we know well. VAB means what? Velocity of A with respect to B. Here F21 is denotes what? It is also nothing but a relative force. Relative force means the force experienced by the second current carrying conductor with respect to the first conductor. So F21 is denotes what? F21 is denoting that the force experienced by the second current carrying conductor due to the field which was produced by first current carrying conductor, which was represented by F21. So substitute the values of B1 here. So what is the value of B1 here? B1 is equal to mu naught I1 by 2 pi r. B1 is equal to what is the value? Mu naught I1 by 2 pi r into I2 into L. So the magnitude of the force F21 is given by mu naught I1 I2 L by 2 pi r. So the magnitude of the force experienced by the second conductor due to the first conductor is given by F21 is equal to mu naught I1 I2 L by 2 pi R. So we derive the expression for the magnitude of the force which was exerted by the first current carrying conductors. Now, force is a vector quantity. Force is a what? Vector quantity. So if we are saying the force is a vector quantity, in which direction it will be acting? In which direction it will be acting? So coming to here, so we have to find the direction of the force which was acting on the second current carrying conductor. So if you apply the Fleming's left hand rule, so here thumb is representing what the force, forefinger is representing the direction of the magnetic field, and the middle finger is indicating the direction of the motion of the charged particle or the direction of the current. So here actually the field will be acting into the plane of the paper. The field will be acting into the plane of the paper, and the middle finger is in the direction of the flow of the current. So my thumb is directed towards what? First current carrying conductor, so that whatever the force experienced by the second current carrying conductor, due to the first current carrying conductor is acting towards the first current carrying conductor. So F21 is acting towards first conductor. So here, if the force is acting towards the first conductor means what? Here the F21 is acting towards which direction? Towards the first conductor. If you apply the Fleming's left hand rule, you will get the direction of the force is acting towards the first conductor. So what is the meaning of the force is acting towards the first conductor means the nature of the force is attractive. The nature of the force is a what? Attractive. See, the first conductor is attracting towards the second conductor means that attractive force is acting towards the first conductor. That means whenever the force is acting towards the first conductor, that means what we have to understand means the nature of the force will be attractive in nature. So when the force will be attractive in nature, so here initially we assumed that the directions of the current in the given two current carrying conductors will be acting along the same direction. That means whenever you got the nature of the force will be attractive means when I1 comma I2 are acting along the same direction, then the nature of the force will be attractive. If whenever the I1 comma I2 will be acting in the opposite direction, suppose if you assume the directions of the current will be acting in opposite direction, at that time there was no change in the magnitude of the force, but its nature will be reverses. So in this case the force will be repulsive. Whenever the directions of the current in the two given parallel current carrying conductors will be acting in the opposite direction, what is the nature of the force is? The nature of the force will be repulsive in nature, but there was no change in the magnitude. Similarly, first if you consider the second conductor, at that time the magnetic field which is produced by the magnetic field which is produced by the second current carrying conductor is equal to, whenever you consider, whenever you assume the second conductor will be placed earlier, whenever we place the second conductor earlier, at that time the second conductor will be producing its magnetic field, whose magnetic field intensity will be given by B is equal to mu naught I2 by, B is equal to mu naught I2 by 2 pi r. B is equal to what? Mu naught I2 by 2 pi r. Now, in the field which is produced by the, second current carrying conductor, if you place the first current carrying conductor, it is also experiences the same force which is represented by F12, F12 means what? Force experienced by the first conductor, due to the current flowing through the second conductor, So, the final expression for the F12 also remains same. F12 is also what? Remains same. So, that value also is equal to, what? F12 is equal to what? Mu naught I1 I2 L by 2 pi r. Now, from this we will write the force experienced by any one of the current carrying conductor, per unit length is given by F by L is equal to mu naught I1 I2 by 2 pi r. F by L is denoting what? F by L is denoting that the force experienced by the any one of the current carrying conductor, per unit length. So, which is given by, that is what? Mu naught I1 I2 by 2 pi r. So, this is the expression for force acting between the two straight parallel current carrying conductors. This is a very, very important question for the board point of view, and for the JEE and NEET point of view also this formula is very useful. So, F by L is denoting what? Force acting per unit length. So, that value is equal to what? Mu naught I1 I2 by 2 pi r. Now, from this, how can we define ampere? So, in this given equation, if you substitute length is equal to 1 meter, and the current I1 and I2 value is equal to 1 ampere, and the distance r value also is equal to 1 meter. So, what I am assuming that we are taking the conductor which is having the unit length, and the distance of separation between the two current carrying conductors also be unity, and if we assume the current which is flowing through the two parallel current carrying conductors will be is equal to 1 ampere, if you substitute all these values in this equation, you will get the force value is equal to what? 2 into 10 power minus 7 Newton. From this, now we are going to define 1 ampere. So, the current which is flowing through the given straight current carrying conductor will be saying as 1 ampere when the force acting between the two current carrying conductors, will be 2 into 10 power minus 7 Newton, whenever those two conductors are separated by the unit distance. So, like this we have to define 1 ampere. Again repeating, how can we define 1 ampere? The current which is flowing through the two parallel current carrying conductors, will be saying as 1 ampere, when these two current carrying conductors will experiencing the force of 2 into 10 power minus 7 Newton, 2 into 10 power minus 7 Newton, when they will be separated by a unit distance. Such type of current we are calling as 1 ampere. So this is the concept of force between two straight parallel current carrying conductors. The next topic is torque acting on a current loop. Which is placed in the uniform magnetic field. So already we know that if any one of the straight current carrying conductor is placed in the uniform magnetic field, by that field over the current carrying conductor, we know that some external force will be acting. But here what we consider a rectangular current carrying loop will be considered. Which type of loop was considered? Rectangular current carrying loop. So here we are going to discuss how much force is acting on the rectangular current loop, and whenever some external force will be there, so some external torque is also producing. Whenever the external torque is acting on the current carrying coil, by that torque, that coil will be rotates. In the given uniform magnetic field. So this concept we are going to discuss. So here our main aim is we have to derive the expression for the torque acting on the rectangular current carrying loop. We have to derive the expression for what? Torque acting on the rectangular current carrying loop. So for that purpose, we consider that two strong magnets, we consider one is the north pole and another one is the south pole. So two strong electromagnets are taken. By that electromagnets of north and south pole, they will be producing a strong external magnetic field. In this strong external magnetic field region, we suspend. So a rectangular current carrying coil, a rectangular current carrying coil which is connected to the power supply, which is connected to the battery. By using this battery, we have to produce the electrical current into this current carrying coil. Now we will see that. So here we consider a PQRS. PQRS is a rectangular current carrying loop. So which type of loop we consider here? PQRS is the rectangular current carrying loop, and here L is indicating the length of the coil and B is indicating the breadth of the coil. So which type of coil we consider? PQRS is indicating the rectangular current carrying loop, and this rectangular current carrying loop is having the length of L, and B is indicating the breadth of the coil. Now, and how the coil will be placed, it is very important. How the coil will be placed in the uniform magnetic field. So here the coil will be placed in such a way that the plane of the given rectangular current carrying coil will be in the direction of the magnetic field. So in which direction, how that coil will be placed, in the uniform magnetic field means the plane of the coil will be existing in the direction of the magnetic field, If you see here, in this PQRS rectangular current carrying coil, So its plane will be xy plane. Suppose if you assume xy plane, this plane will be parallel to the direction of the magnetic field. So the direction of the magnetic field will be acting from where to where? From north pole to the south pole. So its plane is also existing in the direction of the external magnetic field here. So for the direction of the external magnetic field, always PS and QR will be perpendicular to each other. So in the given rectangular current carrying loop, the side lengths PS and QR will be perpendicular to the direction of the magnetic field, whereas the sides PQ and RS will be existing either parallel or anti-parallel to the direction of the magnetic field. So that point we have to understood. So what we will write? The side lengths. So what are the side lengths? QR and SP. Q2R, S2P. These side lengths QR and SP are perpendicular to the direction of the magnetic field. So what we consider here? The side lengths QR, SP are perpendicular to direction of the magnetic field, whereas the side lengths PQ and RS are either parallel or anti-parallel to the direction of the B bar. So what we have to observe while we are placing the coil plane is parallel to the direction of the magnetic field means the side lengths direction we have to understood. If you understood how the side lengths are existing with respect to the direction of the magnetic field, then only we are going to calculate the magnitude of the force which is exerted by the external magnetic field. Once again we consider that what we consider here, we consider PQRS is a rectangular current carrying loop which is placed in the uniform magnetic field. So for the PQRS rectangular current carrying loop, what assumptions we are going to assume? L is indicating the length of the loop and B is indicating the breadth of the loop. Next, how the plane of the coil will be placed? The plane of the coil will be parallel to the direction of the magnetic field. The plane of the coil will be parallel to the direction of the magnetic field. Suppose the magnetic field will be acting from north to south pole means the plane will be like this, not like this. If it is like this, the plane will be perpendicular to the direction of the magnetic field. So here the plane will be parallel means this is the XY plane and the magnetic field is also what? Acting along the same direction. So that is what we called the plane of the coil will be parallel to the direction of the magnetic field. And so we have to discuss about the side lengths. So if you observe here from the diagram, QR and SP. So this is the QR length. So this is the B bar. So QR length is a perpendicular to B bar as well as S2P length is also perpendicular to the direction of the magnetic field. Next, PQ, RS will be either parallel or anti-parallel to the direction of the magnetic field. See, PQ will be in the direction of the magnetic field, RS will be opposite to the direction of the magnetic field. Now we are going to calculate the force exerted by each and every side due to the external magnetic field. See, first coming to the side PQ. Already we told that the side length PQ will be parallel to the direction of the external magnetic field. So already we know one formula, F bar is equal to I into L bar cross B bar, or F is equal to what? Bill sin theta. So what is the expression for the force experienced by any one of the current carrying conductor? So F bar is equal to what? I into L bar cross B bar. So in the case of the PQ length will be in this direction, PQ length, that means that is nothing but breadth, and direction of the magnetic field is also acting in the same direction. So from this what we will say, theta value is equal to 0. So for the side PQ, the distance or breadth will be acting in the direction of the magnetic field, so that the angle between the length and the magnetic field will be is equal to 0. Then the force experienced by the side PQ, the force experienced by the side PQ is equal to 0. The force experienced by the side PQ is equal to 0. Next, coming to the side RS. Coming to the side RS. So here RS length direction will be acting in this direction, R2S length direction will be acting in this direction, and the direction of the magnetic field will be opposite to the direction of the length, opposite to the direction of the length. So here also theta value is equal to how much? Theta value is equal to how much? 180 degrees. Theta value is equal to how much? 180 degrees. Hence the force experienced by side RS also is equal to 0. The force experienced by the side RS are also is equal to 0. That means if you consider the rectangular current carrying loop, which is having the four sides, out of the four sides, the two sides, one is the side PQ, another side is called what? RS. So over the sides of PQ comma RS, there is no force is acting, even though they will be placed in the external magnetic field. So hence the force experienced by the side PQ is equal to 0, the force experienced by the side RS is equal to 0. For that we derived the proof also, right? Next, coming to the side QR. So for the side QR, the length will be in this direction. For the side QR, the length will be in this direction, and the direction of the magnetic field will be like this. So for the side QR, its the length as well as the direction of the magnetic field will be acting right angles to each other, and its length value is equal to L. So that I will directly write the formula: force acting on the side QR is equal to F is equal to Bill sin theta. So that force value is equal to F is equal to what? Bill. That means the side QR will be experiences the maximum force. Similarly, the side SP. For this also, so its the length will be in this direction, and the direction of the magnetic field will be like this. Length will be in this direction, direction of the magnetic field will be in this direction. So that for this also we will write the force experienced by the side SP is equal to how much? Bill also, right? So the sides QR comma SP, being perpendicular to the direction of the magnetic field, they will be experiences the maximum force. That maximum force value is equal to what? Bill. Now, so here I want to actually derive the expression for the torque. How can we define the torque? Torque is equal to force into perpendicular distance of separation between the two forces are acting at the ends of the conductor. Now I want to calculate the direction of the force. I want to know the direction of the force which is acting on the sides QR as well as SP. Now for the side QR, apply the Fleming's left hand rule. So thumb is indicating what force, F is indicating the magnetic field, and middle finger is indicating the direction of the current. If you place like this, say this is the direction of the current, this is the direction of the magnetic field, and so the thumb is acting what? Vertically upwards, or coming out of the plane of the paper. So if you consider this is the length of the given loop or breadth of the given loop. So For the side QR, the force will be acting. The force will be acting out of the plane of the paper. The force will be acting out of the plane of the paper or upwards. I will represent like this. Force acting on QR, that value is equal to what? Bill, which is coming out of the plane of the paper. And the same left hand rule if you apply for the side SP, the force is acting into the plane of the paper. Force is acting what? Into the plane of the paper for the side SP, and for the side QR, force is acting out of the plane of the paper. So, that force direction, I was representing the downward direction, FSP is equal to what? B. FSP is equal to what? B. See here. This force is acting in this direction and this force is acting what? Into the plane of the paper. Now, what is the perpendicular distance of separation between these two forces? The perpendicular distance of separation between those two forces is nothing but the breadth of the given rectangular loop. So, here the directions of the force what we get here by applying the Fleming's left hand rule. So, one of the force is acting into the plane of the paper, another force is what? Acting out of the plane of the paper. Now, how can we define the torque? Torque is equal to the magnitude of the force into, torque is equal to what? Magnitude of the force into perpendicular distance of separation. So, here torque is equal to magnitude of the force is equal to what? Magnitude of the force is equal to what? Bill. On both the conductors that will be experiencing the same amount of the force. Force is equal to what? Bill. And perpendicular distance of separation is equal to breadth. Perpendicular distance of separation is equal to what? Breadth. Now, look at here. Length into breadth. So, area of the rectangle is equal to what? Length into breadth. So, I will write torque tau is equal to what? BIA. Torque acting on the rectangular current loop is equal to tau is equal to B into I into A. B means we know that the magnetic field intensity, I is indicating what? Amount of the current which is flowing through the rectangular current carrying loop, and A is indicating what? Area of the loop. A is indicating what? Area of the loop. A is indicating what? Area of the loop. So, here tau is equal to BIA. This is the torque acting on the loop. Whenever it is consisting of, whenever the loop is consisting of only one turn. If the loop is consisting of n number of turns. So tau is equal to BIA into n. Tau is equal to what? BIA into n, where n is indicating what? The number of turns contained by the rectangular current carrying loop. So this is the expression for torque acting on the rectangular current carrying coil whenever it is placed in the uniform magnetic field. So in this case, what we assumed actually, it is a case 1. Case 1. So in the case 1, what we assumed initially, the plane of the loop will be in the direction of the magnetic field. So that is the case 1. Now we will discuss about the case 2. In the case 2, what we are assuming that the plane of the loop should not be in the direction of the magnetic field. Initially, we assumed that the plane of the loop will be existing in the direction of the magnetic field. Now, what we will tell? So, the plane will be making certain angle with respect to the direction of the magnetic field. In this case also, we are going to derive the expression for the torque acting on the current carrying loop. See. Next one is what? Case 2. So in the previous case already I told that the plane of the coil will be placed in the direction of the magnetic field. The plane of the coil will be placed in the direction of the magnetic field. So, in this case, what is the difference between the previous case and this case? Means here the plane of the loop will be making the plane, this is the plane, this is the direction of the magnetic field. So the plane of the loop will be making an angle theta, with the direction of the magnetic field. In the previous case, this is a plane, this is the direction of the magnetic field. The plane will be existing in the direction of the magnetic field. Now, what we assume that the plane of the given loop, will be making certain angle with respect to the direction of the magnetic field. So like that we have to assume. So here we assumed that two angles. First one is what? Theta. First one, theta. What is the theta indicates here? Theta is indicating the angle made by the plane. Theta is indicating what? Angle made by the plane with the direction of the magnetic field. So what is the theta I assumed here? Theta is indicating the angle made by the given plane, or plane of the rectangular loop with respect to the direction of the magnetic field, Now, for the given plane, so this is the plane. For the given plane, I am drawing a normal. For the given plane, what? We are drawing a normal. So, for the given rectangular loop PQRS, I am drawing a normal. So, this is indicating normal which is drawn onto the given rectangular loop. And this normal is making an angle alpha. With the direction of the magnetic field. So here we have to define the two terms. One is the theta. What is the theta here? Theta is indicating the angle made by the plane of the loop with respect to the direction of the magnetic field. So what we define here, theta is indicating what? Theta is indicating the angle made by the given plane with the direction of the magnetic field. And another angle is the what? Another angle is alpha. What is the alpha here? Angle made by the normal to the direction of the magnetic field. Angle made by the normal of the given loop with respect to the direction of the magnetic field. These are the two assumptions we assumed in this case. The same explanation as we told in the case 1. So in the case 1, what we told? The force experienced by the sides, PQ and RS. The force experienced by the sides PQ comma RS will be is equal to 0. Because in that case PQ and RS will be parallel or anti-parallel to the direction of the magnetic field. But in this case, these sides PQ comma RS will be making certain angle with respect to the direction of the magnetic field. That means they will be experiencing some force. with respect to the magnetic field. But if you consider their directions, so they will be experiencing the same magnitude of force. That means the force experienced by the PQ, will be is equal to force experienced by the RS. That means the force experienced by the PQ portion will be equal in magnitude with respect to the RS. But these forces are acting in opposite directions. Whatever the force experienced by the side PQ comma RS, they will be acting in the opposite directions. As a result, these two forces are cancelled out. These two forces are what? cancelled out. The difference between the first case and the second case is, in the first case directly the force experienced by the both the sides PQ comma RS will be is equal to 0, but in this case the magnitude of their forces will be, remain same, but they will be acting in the opposite direction, hence those two forces will be getting cancelled out. Those two forces are getting cancelled out. Now coming to the sides P, S and QR. Coming to the sides QR and SP. Even though the plane will be making certain angle, this QR length and SP length is always perpendicular to the direction of the magnetic field. If you look at the diagram, this is the QR length, this is the direction of the magnetic field. QR is perpendicular to the magnetic field, and S2P is also perpendicular to the direction of the magnetic field. That means the length QR, the length SP are perpendicular to the direction of the magnetic field. The length QR and the length SP will be perpendicular to the direction of the magnetic field. So whenever their length will be perpendicular to the direction of the magnetic field, those portions will be experiences the maximum force. Those portions are getting maximum force. So the force experienced by the QR part, the force experienced by the SP part will be remain same in a magnitude. Their magnitude value is equal to what? BIL. Why BIL? I into L bar cross B bar. So L is perpendicular to B bar. Theta is equal to 90. So that these portions are experiences the maximum force. Already we told what are the directions of QR comma SP. The directions of QR is acting out of the plane of the paper. Out of the plane of the paper, as well as the force acting on the side SP will be acting into the plane of the paper. So that their force's direction is represented by, so here this is the force experienced by the QR, which is acting into the plane of the paper, the force experienced by the QR portion which is acting into the plane of the paper, and the force experienced by the SP portion which is also acting into the plane of the paper, because the coil will be rotated through certain angle. So this portion, the distance of separation between the sides QR and SP will be making theta angle with respect to the direction of the magnetic field. Once again, because the coil will be rotated by an angle theta, so the sides of the coil, the breadth of the coil is also making theta angle, with respect to the direction of the magnetic field, that only we wrote here. So if this is the horizontal direction of the magnetic field, so this is indicating what? Horizontal direction of the magnetic field. So thus breadth of the coil will be making an angle theta, with respect to the direction of the magnetic field. And already we draw a normal. Normal means what? This normal will be perpendicular to, either length as well as the breadth also. So here this normal will be perpendicular to the coil. That normal will be what? Perpendicular to the coil. Already we assumed that a normal will be making how much angle with respect to the direction of the B bar. This normal will be this normal will be making alpha angle, this normal will be making alpha angle with respect to the direction of the B bar, with respect to the direction of the B bar. This diagram is important, we have to understood carefully, because the coil will be rotated through an angle theta, so this side of the coil will be making an angle theta with the direction of the magnetic field. And already we assumed that if you draw a normal, suppose, so this is the coil, so this length is a what, this is indicating what, side length, this length is indicating what, breadth. If you draw a normal, this normal is a perpendicular to the breadth, this normal is also perpendicular to what, length also. So that only we told here. So here AB is indicating, AB is parallel to the breadth, AB is a what, parallel to the breadth. So this is the normal, this normal is a what, perpendicular to the side length, Now from this diagram what we will write? From this diagram we will write theta plus alpha is equal to 90 degrees. From this what we will write? Theta plus alpha is equal to what? 90. This normal is a perpendicular to the side AB. That's why we wrote that theta plus alpha is equal to what? 90. Now, to calculate the torque here also, So, to calculate the torque, what value we needed? So, torque is equal to what? Torque is equal to magnitude of the force into perpendicular distance of separation between the two parallel forces. See, here this force is acting in this direction and this force is acting into the plane of the paper. So between these two forces we have to calculate the perpendicular distance of separation. So to find the perpendicular distance of separation, here I form a right angle triangle. So this force is acting in the vertically upward direction, this force is acting in the vertically downward direction. So these two forces are the parallel forces. Whatever the separation between A and C, that AC length will be giving the perpendicular distance of separation. So torque tau is equal to, F means what? Magnitude of the force is equal to what? Bill. And R perpendicular means what? AC. R perpendicular is equal to what? AC. Now you will look at the diagram. If this angle value is equal to theta, which is made with the total line, this angle is also equal to theta. That angle also is equal to what? Theta. Can I write the theta here? It is also parallel to this one. So the angle made by the line AB with respect to the horizontal is equal to theta, means the line AB is also making the same angle with the another horizontal AC, which is a parallel to the above dotted line. So here one right angle triangle was formed, A, B and C. This is the theta, this length is equal to what? B, and this length is equal to what? R perpendicular. So from this I will take cos theta value. Cos theta is equal to adjacent side. In the adjacent side, what is the value present? R perpendicular by hypotenuse value is equal to what? B. So from this I got that R perpendicular is equal to what? B sin theta. R perpendicular is equal to what? B sin theta. So substitute this R perpendicular value in that required equation. Tau is equal to what? BIL. R perpendicular means what? B cos theta. So this value is equal to what? B cos theta. Now here B into I into L into B. So here theta plus alpha is equal to what we wrote here? Theta plus alpha is equal to what? 90. Theta plus alpha is equal to 90 means theta value is equal to 90 minus alpha. Theta value is equal to what? 90 minus alpha. So I will substitute the value of theta, cos of 90 minus alpha. cos of 90 minus theta, it is in the first quadrant, so that cos of 90 minus theta value is equal to what? Sin alpha. So here this value is equal to bi into length into breadth is nothing but area of the loop, cos 90 minus theta is equal to what? Sin theta. Here cos of 90 minus alpha will be there, so that value is equal to what? Sin alpha, So this is the expression for, this is the required expression for torque experienced by the rectangular current carrying loop, whenever it is placed in the uniform magnetic field. And moreover, here, see here, this is the general equation. Now I will convert this equation into another form. Already we know that if a current carrying loop is placed in the uniform magnetic field, it's a magnetic momentum formula. M is equal to I into A. M is equal to what? I into A. Magnetic momentum of the loop is equal to what? I into A. A is indicating what? Area of the loop. So in the place of I into A, I will write tau is equal to B into M into sin alpha. So here, by the definition of the cross product, A bar cross B bar is equal to what? AB sin theta. So it is also in the same form. So that the torque was represented in the vector notation. Tau bar is equal to M bar cross B bar. Tau bar is equal to what? M bar cross B bar. What is the M bar? Magnetic momentum of the given rectangular loop. And B bar is indicating what? B bar is indicating the direction of the magnetic field, and alpha is indicating the angle between these two vectors. How alpha is angle between these two vectors means, for a given loop, the direction of the magnetic moment is always existing in the direction of its normal only. So that in the direction of its normal only, M bar will be acting. In which direction M bar will be acting? The magnetic momentum of the rectangular loop. Will be existing in the direction of the normal. Therefore, the angle between the M bar and the magnetic field B bar is nothing but alpha. So this is the reason why we are writing tau bar is equal to M bar into B bar, means the M bar is existing in the direction of the normal of the loop. That's why we wrote tau is equal to either MB sin theta or MB sin alpha or M bar cross B bar. So this is the final expression for the loop. If the loop is consisting of n number of turns, so this equation becomes to what? Tau is equal to n into, for n number of loops, n into m into b into sin alpha. So this is the final expression for the torque acting on the rectangular current carrying loop, whenever it is placed in the uniform magnetic field.